This YouTube series will cover material that we cover in our Introduction to Astronomy class, from a meteorite found in Antarctica from the planet Mars and the search for life, all the way through to supernovas and black holes. There is no planet in the solar system that we know more about than the planet Earth. If you remember from our discussion of the formation of the solar system, planet Earth was formed as one of the terrestrial planets, one of the small-end planets that differentiated, then lost its atmosphere to the powerful solar wind. And we also learned from average density that the 2% other ball of molten material that formed the Earth then differentiated again and sunk down to an iron core, which represents about half of the Earth. So the Earth has an iron core. And it turns out, interestingly enough, that the iron core is liquid on the outside. So it's a liquid iron core on the outside that's circulating around, and there is a solid iron core on the inside. That is the result of the intense pressure at the center of the Earth. So even though it's plenty hot to be liquid, it's solid because it's under intense pressure. So the liquid iron core is circulating around. We've got this cooling from the outside molten ball. It begins to form a crust. In between, we've got a mantle. So we've got a crust, a mantle, and a core. This giant liquid outer core, this solid inner core rotating around. And in fact, the solar wind, which blew off the Earth's first atmosphere, remember the Earth's first atmosphere was this giant halo of hydrogen and helium, the solar wind still exists, but the presence of the liquid iron circulating around inside the Earth, this strong conductor, iron is a good conductor. As the liquid sloshes around, it generates a charge, which generates a giant electromagnet, creating a north and a south magnetic pole, which was not present in the early Earth. It provides an invisible cocoon to protect the Earth's atmosphere today. So the solar wind still exists. It's powerful. It's racing off the sun. But the solar wind tries to peck off our atmosphere, but instead is shunted to the poles. These charged particles go to the poles where they sit, and those charged particles sit here at the north and the south pole, and those charged particles, deflected by the magnetic field, sit at our poles and excite the gases in our upper atmosphere, creating the aurora borealis and the aurora australis. So, if you've ever seen the northern and southern lights, that is the invisible protection that exists as a result of our liquid iron core. The question you might have is, so where did the atmosphere come from if it was blown away? The first atmosphere of hydrogen and helium gone to the solar wind. The second atmosphere created by volcanoes. The early Earth, this is an exact drawing, the early Earth has thousands of active volcanoes spewing gases that produce the Earth's second atmosphere, an atmosphere rich in water vapor, carbon dioxide, nitrogen, and argon. Much of that water ends up forming clouds and raining down and forming the early oceans between these mountains. As the continents coalesce, the oceans form in between. In fact, it's generally thought that about half the water in the Earth's oceans comes from volcanoes, and about half the water comes from the continual influx of cometary water from outer space. So we've got ourselves some oceans. We've also got an atmosphere rich in water, carbon dioxide, nitrogen, and argon, but that's not the atmosphere we're breathing today. The Earth's third atmosphere, the atmosphere we're breathing today, is rich in nitrogen. It's about 78% nitrogen. It's about 21% oxygen. And it's about 1% argon. So 21% oxygen, 1% argon, and 0 to 4%, depending on the amount of water trapped in the atmosphere at any given time, water vapor. This is the Earth's third and present atmosphere. Some of you may be looking at this and saying, well, wait a minute, what about carbon dioxide? We hear so much about that in terms of climate change, and rightfully so. Carbon dioxide is a heat-trapping gas. The carbon dioxide that we've had for millions of years has been about 0.027%. In recent times, it has increased to be over 0.04%. That's the concern, because this gas, carbon dioxide, is a heat-trapping gas that forms a warmer and thicker blanket around the Earth, which leads to what we call climate change or global warming. The point is, the amount of carbon dioxide in the atmosphere is a small but significant amount, and leads to, with its heat-trapping ability, the warming of the Earth. Of course, carbon dioxide is created in large part by the burning of fossil fuels, hence the movement towards more renewable resources in the form of wind and solar energy, battery-powered cars, that could potentially pull us back from thickening that blanket of heat-trapping gases. The point is, carbon dioxide is a small percentage of the overall atmosphere. The atmosphere we're breathing today is loaded with nitrogen and oxygen and a little bit of argon. Similar, but not exactly the same to the atmosphere we had in the early Earth. You'll notice the nitrogen is here. The oxygen is, the water, is there. The argon is there. The big change is we go from a CO2-rich atmosphere, tens of percents of carbon dioxide, prior to human beings, and we move to an oxygen-rich atmosphere, one with which mammals can make use of. How did that happen? How did the Earth go from a carbon dioxide-rich atmosphere to an oxygen-rich atmosphere? It has everything to do with life. Microbial life, specifically in the Earth's oceans, blue-green algae, cyanobacteria, takes carbon dioxide, removes the carbon, and spits out a waste product in the form of oxygen. It is life. That the signature of life on Earth is the oxygen-rich atmosphere. No other atmosphere in the solar system, or that we've detected around any planet, has an oxygen-rich atmosphere. That doesn't mean it isn't out there. In fact, that may be an indicator of some very interesting chemistry. In our case, the chemistry we call biology. So the atmosphere moves in this direction. That is the current atmosphere of the Earth, protected by the magnetic field. The continents continue to move, and driven by volcanism, driven by heat welling up from the interior. In fact, that was only figured out just roughly 100 years ago. A guy by the name of Alfred Wegener, a character much like the Copernicus and the Galileo and the Kepler characters of the past. Alfred Wegener suggested that in fact the continents might one day have been merged together and then split apart. He called that one giant supercontinent Pangaea. He coined the term continental drift. He argued that volcanism pushed the continents apart. And the Earth, being an active and geologically alive planet, pushed the continents apart, responsible for earthquakes and the formation of mountain ranges and volcanoes on the Earth today. Certainly a topic of discussion in geology class. The point is, if you look around the Earth today, you see a world that is much less geologically alive, though still so. We've got earthquakes, we've got volcanoes, but dramatically fewer than we had in the past. In fact, we even have craters on the surface of the Earth, though not many. The reason for that is, of course, that the Earth's surface is geologically alive. It's constantly renewing itself. We've got weathering and erosion and volcanism. If we turn our gaze to another large body, specifically the one called the Moon, we will find that that's entirely different. The Moon's dominant geologic process is impact cratering, and we'll talk about that in our next segment.